All right, this should be recording. Hi, good morning and good afternoon, everyone. This is a helpful video supposed to guide you on how to make your flashcards and how to tackle problems at 5, because we've been breezing through a lot of these reactions and a lot of people are confused, which is understandable. This is organic chemistry. This is the actual meat and nitty-gritty stuff of chem that's notorious for not being fun for people. And I'd really pay attention because a lot of these reactions, if you're pre-med, it will show up on the MCAT. That's why you need to make these flashcards and hold on to these flashcards. But the goal of this video is just to tackle and just go through what you need to know, what you don't need to know, and some helpful tips when doing chapter 6 and probably some chapter 7 reactions. Okay. Now, if you're watching this on YouTube, which all of you are because no one's in here, a helpful idea is putting it on 1.5 speed, because I am a little bit of a slow talker because I want to emphasize certain things. And I know like some people trail off in the video, but let's just not worry about that. Just do whatever's right for you. All right. So let's go ahead and record, or not record, share my screen. So you guys should be seeing my screen right here on my iPad. Okay. Now, let's just get one thing out of the way. You don't need to know every mechanism for the test. All right, there's 3 you have to know, and 2 of them are pretty much the same thing. Granted, the 3 you have to know are relatively complicated, relatively big, a lot of electron transfer or proton transfers, but I take that over the stuff like boration, MCPBA. You do not need to know these reactions or the mechanisms. You just need to know what they do and what they don't do. All right. So with that out of the way, let's talk about the big 3 you do have to know. And I always call these the big 3. Because the big 3 are relatively the same deal. Like you have an electrophile that adds here, and then the nucleophile goes where that carbocation is. So let's go ahead and just identify them first. Your big thing is going to be HX. So that includes HCl, HBr, HI. Okay. That's the first reaction you learned. Next is hydration. H2O, H2SO4. All right. Next is solvation. CH3OH, H2SO4. These will be on the test and will pretty much exactly be, all right, where are the electrons moving? Draw every lone pair. Where's the rate determining step? What are the spectator ions? What's the final product? Or how do you get to the final product? Because usually the format will be reactant, reagent, or reagent, no, reactant, reagent, and then product. Draw the mechanism on how we got that. And it's pretty tough. You can't leave anything out. We'll put like the lone pairs on a single atom would be worth 1 point possibly, because we got to make sure you know what's moving, what's not moving, okay? Now, the big things to note, just right off the bat, that you should keep in the back of your head is 1. All of these have carbocation intermediates. If it has a carbocation intermediate, shift happens, because carbocations are opportunistic, okay? If they're next to a tertiary or quaternary structure, it can shift, it can make itself more stable, because you have no idea how relatively unstable carbocations are, all right? It's a lot of energy that creates an unstable empty p orbital for a carbon, okay? Now, carbocations, well, first off, they shift. Second, there's no stereochem. You can draw everything as just sigma bonds. We just care about connectivity because they all rotate. And you might be thinking, why doesn't it have stereochem? Well, if you remember, carbocations have an empty p orbital, all right? They have an empty p orbital. And if that carbocation is an actual phase of matter in that reaction, that carbocation is spinning on that sigma bond, and there's 2 faces a nucleophile can add on to. So stereochemistry doesn't matter, because you'll get a receiving mixture wherever it adds. And we'll get to that later in lecture. So don't worry about what I just said. So there's no stereochem. All right. Oh, what's the other thing? Shift happens. There's no stereochem. Man, I'm blanking. I think that's it. Shift. No stereochem. Oh, there it is. Rate determining step. One of the questions that they'll always ask, and you have to be sure to read the instructions, is on the mechanism page of the test. You have to write the rate determining step. You'll see that in 2017. You might see that on some of the 2021 exams that one of the TAs will post up. Now, for that rate determining step, it's pretty much always going to be the formation of the carbocation. Because remember, the rate determining step is the biggest hoop or loop with the activation energy on the energy diagram. All right. So give you an idea, all right? There's an energy diagram, reactant, product. This is your highest hoop, the biggest activation energy. And that is usually that transition state as it makes the carbocation intermediate, okay? Carbocation intermediate is pretty unstable. That's rate determinant step usually. Not always, but the general trend for Chem 1 and 2, rate determinant step is usually the formation of the carbocation, okay? That out of the way, let's go ahead and start on our mechanism. The first step is, you might think, let's move the electrons around. No, you don't need to do that. You want to be thorough. Let's be thorough. Let's identify what we're dealing with. Let's look at our bridgehead carbons like we did for cis and trans stuff, okay? This carbon right here, what's the substitution pattern for that? It's connected to 1, 2, 2 carbons, secondary. What about this one? It's connected to 1, 2, 3, 3 carbons, it's tertiary. You have to be sure to draw the substitution pattern because it's not always plain and simple. There might be shift happening and you have to know, all right, where does the carbocation want to be? What's going to be reactive with what? I don't know why I have that. So let's go ahead and just draw it out. Let's draw that this pi bond breaks. It opens up, it grabs this hydrogen right here. The electrons go to that chlorine, okay? And you might be thinking, first off, why is it grabbing hydrogen? Well, partially positive, partially negative, all right? Pi bond is an electron dense region. Electrons, where are they connected to? Opposite attract, negative charge, electrons, positive charge, whichever one's more positive will be what? The electrophile, because it likes the electrons, okay? So if it likes the electrons, the hydrogen's the one that's partially positive, is going to attach there. So I redrew the carbon structure without that pi bond. And I know, all right, out of the 2 bridgehead carbons, the hydrogen is going to be in the least substituted one. Electrophile goes on the least substituted. You might be thinking, why? Why isn't it not on this carbon? All right. Well, remember, when you have that hydrogen being attached, you form the carbocation intermediate. Just going to do it right here, rate determinant step. Okay. So you form the carbocation intermediate. It's a rate determinant step. It wants to be opportunistic. It wants to be on the most substituted carbon because it's the most stable, the greatest hybrid conjugation of neighboring carbon groups. Okay. So the carbocation does not want to be over here. It wants to be on the tertiary. Plain and simple. Okay. Now you have a spectating Cl, chloride ion, negative charge. And would you look at that? Negative formal charge, positive formal charge. Opposites attract. The arrow has to come from the electrons. Remember, arrow is always source from the electrons. If you draw the arrow backwards, it's wrong. So know the direction where the arrows go. The source is always going to be electrons. Right here, even the source coming from electrons. So the electrons are coming from chlorine and they attach to that empty p orbital and form a pi bond. So what do we get? That attachment creates chlorine and H. It adds HCl across the double bond. And note, Cl has to be on the right side because the nucleophile goes to wherever this most substituted carbon is. This is Markovnikov, right? Because Markovnikov, carbocation is on that most substituted carbon, right? Now, you look over here, remember, okay, shift happens for carbocation intermediates. Something I might have forgotten to say right here, again, is tertiary. The gold standard for carbocations is tertiary, right? Because you know there's primary, secondary, tertiary, quaternary. Carbocation is like tertiary. You may think, why not quaternary? Well, quaternary carbon, that's just 4 carbon bonds. That's quaternary. There's no room for a hydrogen. That's already a complete octet. It doesn't need a positive charge. It's quaternary. However, for tertiary, this is a carbocation. That's pretty stable. Carbocation exists there. And tertiary is the gold standard for a carbocation, okay? All right. With that in mind, let's continue forward. So something you might see in your problem set, and you might see on the test, is something similar to this. Cl and I. Well, what the shit? What do you do? Well, take a step back and identify. We have an alkene reacting with Cl and I. Is it polar or non-polar? It's polar. And you kind of have to think intuitively, well, chlorine is more electronegative, partially negative. Iodine is partially positive, even though it's a halogen compared to chlorine. It's not very electronegative. So if you have something like that, well, where will these electrons go? Chlorine or iodine? Electron, which one's the electrophile? Partially positive one, right? This is the iodine. So electrons go back to the chlorine. All right. Well, let's run it back. Okay. Where does the iodine attach to? That might be the question. Well, the iodine is the electrophile. So it is the equivalent of H. So electrophile adds to the less substituted. Less E, more nu. Less substituted electrophile, more substituted nucleophile. Okay. So less substituted would be that iodine. And now you have a carbocation intermediate. Now you might be thinking, okay, carbocation intermediate, no stereochemistry. It can shift. But look at it, it's tertiary. No shift needed, right? So your spectating chlorine can just go right on into there and enjoy its time. You added a Cl and an I across the double bond. There you go. All right, let's kick it up a notch. Let's do some hydration. Now, for hydration and solvation, there is a minor step that happens in the solution outside of the alkene. So sulfuric acid, OH, OH. Excuse me. I'm gonna draw out the sigma bond just for this one. And then H, well, the moment you have a solution, of H2O and H2SO4. That's dilute sulfuric acid, all right? That's gonna be pretty acidic. So if it's acidic, then you're gonna have like a bunch of protons flying everywhere. So the protons, well, if you know from Gen Chem, forms H3O plus. So just on the side, lone pairs attached to the electrophile. All right, because this hydrogen's positive charge or partially positive charge, likes electrons. Okay, electrons go back to that oxygen, and then we'll get H3O plus. I'm going to draw this one out, H3O plus. Positive charge. Pay attention to that positive charge. Okay, and then you have HSO4 minus. Now the thing with sulfuric acid, it's that this HSO4 minus, now nucleophile. The moment we just draw, you got to keep it there. The moment we draw that as a product, just don't worry about it. Don't worry about it. And now we want to focus on that hydronium ion. Okay, so now that we've reacted it, we have hydronium ions floating in the solution because, again, it's acidic. When you put an alkene in there, what do? Well, what we've normally been doing. Double bond, you have H2O plus, H, lone pair. Double bond goes in, attacks that electrophile, positive charge here, and then the electrons go back to the oxygen. You might be thinking, it just got that hydrogen. Why is it going there? Don't worry about it. Just know the proton on that sulfuric acid will find its way to the alkene through the medium that is water, or through the solution. Okay. Don't worry about what adds to it. Just know that hydronium, it will take the hydrogen from the hydronium. Okay. Don't overthink it. Don't overcomplicate it. Just know, you just try to memorize this. Okay. So that goes there. Okay. So we get our rate determining step. As we form a carbocation, you might be thinking, well, this isn't a positive charge on the oxygen. It's not a carbocation. That's an oxygen cation. Okay. Okay. Now, across the double bond, look at our bridgeheads. What do we look at? We're looking at secondary and primary. The primary one, the less substituted, gets the electrophile, less E, more nu. Less substituted, hydrogen. Carbocation goes here. Now let's take a step back and recognize, all right, carbocations, they can shift. If that's secondary, right here we have a tertiary carbon. We have a carbon, CH3, CH3. Well, look at this carbon right here. There's a hydrogen on there. I'm thinking, how's there a hydrogen on there? Well, remember from test 1, line structures, you have to complete the octet. If you have 2, 4, 6 valence electrons, hydrogen, that other sigma bonds needed there. CH connected to 3 other carbons, okay? So there's a hydrogen there. I'm just gonna draw it right here on the subside, all right? And that's tertiary, again, tertiary. Well, what does it want to do? It's opportunistic. It'll want to be on that tertiary carbon. So what will it do? Well, this carbocation will trade places with the hydrogen. All right. And that'll form this. H again, that's from the hydronium ion, and then carbocation right here. There's no second one. Just carbocation. Okay. You're thinking, why is it a hydride shift? Why not a methyl shift? Well, if it traded with a methyl group, all right, if this methyl group was over here, that would be a secondary carbon. So that's kind of not, why would you do that? Just, it's easier to trade the hydrogen over. It's a smaller group. And if you traded the methyl over, you would be trading the tertiary substitution. So remember, tertiary is the gold standard. Okay. So if it shifts over there, now what do we have? We have our nucleophile still floating around, H2O. Okay, H2O. I was writing in every step, just keeping consistent. Now you have lone pair going to the open nucleus. Nucleophile, there's relatively open p orbital that is exposing the carbon nucleus. So it's going to attach there. Okay. So you're going to get O, H, H, positive charge, that hydrogen right there. Okay. Now what do we do? Well, we saw a positive charge on that oxygen. Well, it's protic. We got to get rid of that hydrogen. So another solvent, it could be the HSO4 minus and preferentially another water right here, or any convenient base, perfectly acceptable, just a B for base, not boron, base, that comes in and takes that electron. All right, that arrow is just supposed to be like a would-be, or hydrogen. That would be a would-be hydrogen. But for this case, I'm just going to do H2O just to keep it consistent. All right, it'll take that, and then this single bond would go back there. Okay. We would get H, O, H. Okay. And then as a byproduct, we'll get the protonated water, H. That's it. We essentially added, look, an OH and an H across the double bond. But note that carbocation shifted because carbocations can shift. Shift happens. But we still added a water across the carbon compound, okay? Maybe thinking, well, if the product is H3O plus, what else do we do with it? Well, the answer is nothing. Don't worry about it because, again, it's an acidic solution. You have protons flying around. You already have H3O plus floating around there. Don't overcomplicate the stuff. Just memorize it and understand where the electrophile goes, where the nucleophile goes, because it's okay. It's okay. Don't overcomplicate it. It's already a lot. Okay. Now, solvation, good news, it's the same exact thing. Because if you think about it, water is just an OH that's connected to a hydrogen. It's the most simple alcohol ever. So if we just treated that CH3 or whatever R group, it could be ethanol as an H, just ignore it. It doesn't play any role in the reaction. Then that's how we proceed with it. That CH3 or whatever alkyl group is not protic. Because what's more acidic, the H on an oxygen or the H on a carbon? It's the H on the oxygen. The oxygen is more electronegative. Okay. So we have our double bond. Well, first off, let's go ahead and draw that supplementary reaction that happens just in the solution. HSO4. I'm not going to draw the lone pairs just because HCH3. That's methanol. Okay. Swoops in, takes that hydrogen. Electrons go back to the HSO4 minus. We get a protonated CH3. H lone pair positive formal charge. And when you draw this on the test, do not forget your formal charges. That is another point. Do not forget the formal charges. And then we get HSO4 minus. And I'll just leave that be in the solution. It's ignore it. Now we have that protonated methanol in the reaction. HOH CH3, double bond breaks. Where's it going to attach to? The hydrogen. Hydrogen's the electrophile. Sigma bond goes back to the oxygen. So we get, right, our double bond is across, straight across, we got tertiary. We got secondary. Okay. So where's the electrophile going to go? Less substituted, E, more substituted, nu. Less E, more nu. So less substituted gets that electrophile. Carbocation forms wherever that electrophile isn't, because there's a void. Carbocation, we'll look at it. It's on a tertiary carbon. Will it shift? It can shift, but it won't, because tertiary, that's what it likes. It doesn't need to. It doesn't need to make it complicated. So now we have a floating CH3OH just floating around. Well, we got nucleophile. Electrons go to where they is, to where they ain't. Okay. So we get, oh, by the way, this is the rate determining step. Formation of the carbocation. OH CH3H. And if you look at this one right here, well, let's go back up. That's pretty much the same thing as this. Obviously, the top one is shifted, but let's not worry about it. Let's just focus on the concept as a whole. An OH with a positive charge, and then an OH with a positive charge. Whoops. It's the same mechanism. And just like before, you have a convenient base, and in this case, it'll be another methanol, because it's a methanol solution, CH3H. It'll come in and take that hydrogen and then just deprotonate it. So our products would be CH3OHH, positive charge, protonated whatever solvent was, and then our product, which is now just OCH3, an ether, and then an H. That's it. That's literally it. All right. And again, you have a protonated methanol. What do you do with that? Nothing. It's an acidic solution. Those are the three mechanisms you have to know or memorize. Okay. No shift needed, or shift needed. No stereochemistry needed, because remember, those are carbocation intermediates that can rotate. So syn addition, anti-addition doesn't matter, because it's either direction of that pi bond. Okay. And the rate determining step is the formation of the carbocation. Okay. There's multiple steps. The rate determining step has to be one of them. It's going to be the formation of the carbocation. Now let's look at everything else. Everything else, thankfully, you don't need to know the mechanism. You just need to know what it does. So for the flashcards, what I would literally do is I would make a drill. I have all these reactions on a piece of paper or flashcards. I would take 10 or 15 minutes out of my day and just look at them. And for the drill, I would put the paper away, draw the reactions, and I have to draw, okay, this to that, these are the reactants. And you have to draw the exact reagent and the solvent, whatever it's in. You have to know it. And straight up, it's memorization. This is the work you have to put into OChem. You just have to memorize it. All right. And you'll need to memorize it for the final, and you'll need it again for semester 2. And you'll need it for the MCAT. Literally, if you're pre-med, this is the work you have to put in. There's no way around it. Just memorize it. Okay. So for this one, Br2, CH2, Cl2. First thing to note, aprotic, all right, is an aprotic solvent. And another variation could just be CCl4. That's another variation, but it's aprotic. So it's aprotic. First off, it adds 2 BRs across a double bond. Anti-addition. Okay. Anti-addition, so you need, yeah, and no shift. And with that in mind, all right, let's redraw our thing without that double bond, because we know, all right, anti-addition, top half, Br. Bottom half, Br. Anti-addition. And then for that methyl group, I just draw like the respective stereochemistry, because if the Br has to be on one plane, the methyl group has to be on the other plane. All right, that's the product. And it doesn't have to be exactly the same. You can, or a perfectly acceptable one would be Br, CH3, then Br. Any one of them is accepted, okay? Because, well, I mean, you can't go wrong if you're right. And in all honesty, yeah. Actually, I don't need to add anything. Either one will be accepted because you just need to show that it's anti-addition. And just to give you a little bit of what we're trying to look at, okay, let's draw the Hayward structure for this cyclohexene, or was cyclohexene. Br added on one plane as a bromonium ion, and the other Br has to attach somewhere on the opposite end. Doesn't matter which one, but it adds on the other end. You just have to show that's anti-addition. That's it. That's all you have to do. And then obviously, like wherever your methyl group is, just a keeping system, but don't worry about it. You just have to know the product. No mechanism needed. You don't need to know about the bromonium ion. It's helpful to know that it's anti-addition, but no, this is what, or the Br and the Br, that's what's being added. The anti-addition, that's what you need to know. And there's no shift. It's, even though it's not concerted because there's an bromonium ion intermediate, there's no shift because that triangle formation can't move around. Okay. Now let's look at Br2 and H2O. This, you have a protic solvent. You have an alcohol substance. So first off, it adds a Br and an OH. Okay. Anti-addition. No shift. And additionally, this is Markovnikov. Everything. What about up here? This one Markovnikov? Yes and no. You're adding the same atom across. Markovnikov does not matter here. Okay. Okay. Well, now that we know what we're trying to add Br and OH. It's Markovnikov, anti-addition. So let's just redraw our product. Okay. Anti-addition, Markovnikov. So this is tertiary. Secondary. What's Markovnikov? Which one's going to take the most substitute carbon? It's going to be OH. Are you thinking, why is it OH? Because bromine's a halogen and oxygen is just a weird group 6 atom. Well, look at it. OH is literally a strong base because that's what we know from Gen Chem. And Br is just the conjugate base of a really strong acid. It's a really weak base. So which one is going to be more nucleophilic? It's the OH. Okay. That's how I look at it. OH and then dotted line Br. That's all we have to do. And then just on the opposite plane, draw that methyl group just to keep it consistent. And that's your answer. All right. I'm going to pause this real quick and pull it up. Let me pause recording. I'll be right back. All right. I should be, yeah, okay. Resume recording. All right, I'm back. Just had to pull something. Okay. So like I just said, adding the OH and Br across, OH is Markovnikov and it's anti-addition. So all I have to do for your test, just write what the product is, and that's what you write on your flashcard, the top three right here. Let's move on. H2, PDNC. Okay. Well, it adds H and H, two H's across a double bond. Okay. Two, it's an addition. It's concerted reaction. Not only is it concerted, is it Markovnikov or anti-Markovnikov? Yes and no, because it's the same atom, two hydrogens. It doesn't matter which one's a Markovnikov or not. So let's redraw our thing, or redraw our compound, but just without the double bond. So we are adding an H and an H. It's an addition. So we're going to do wedged or wedged, hydrogen, hydrogen. That's it. There's no other methyl group we have to count for. Or methyl group as in like we have to show the stereochem. I guess I can show the stereochem for the other hydrogens that were already here. The black hydrogens and the dotted lines are the same hydrogens right here. Okay. It's an addition of hydrogens. That's it. That's all you have to do. Excuse me. Yeah. No, Markovnikov doesn't matter. That's it. That's what you put on your flashcard. Okay, now let's take a look at boration. Now, we just did this mechanism, something you do have to memorize. And if you know H2O, H2SO4, hydration, we add an OH and an OH across a double bond, OH being Markovnikov. So we know, all right, first off, an OH and an OH or an H is being added. Okay. 2, it's Markovnikov. 3, shift happens. All right. That's it. There's no syn addition or anti-addition because there's no stereochemistry for carbocations. So let's redraw our product or our reactant, but without the double bond. All right. Tertiary, secondary. All right. Well, what do we know about this? We add an OH and an H. It's Markovnikov. OH goes here. H goes here. Because remember, OH is our nucleophile. It's going to add to the most substituted carbon, which is this top one, the tertiary one, because it's Markovnikov. Not only that, we don't have to do wedges or dash because either one will work. There's no stereochemistry needed. Okay. And yeah. Now for boration, this is something, again, kind of a weird reactant. You will have to know BH3THF, and you will have to know H2O, NaOH, and H2O2. Why do I have to do that? It's science. You're a STEM major, or you're taking a STEM class. You just gotta BH3THF, H2O, NaOH, H2O2. All right. First off, adding an OH and an H. That's what you put on a flashcard. OH and an H. 2, anti-mark. 3, shift doesn't happen. Shift doesn't happen. It's concerted. Or, no, well, not really. But the addition of the electrophile and the nucleophile is concerted. The nucleophile or the electrophile being the boron. Don't worry about it. Just know it's anti-mark. It's really easy. You don't have to know the mechanism for it. Just know it's anti-mark. You're adding an OH and H, anti-mark. Less substituted gets the OH. Redraw our thing. Hold on. Where are you? I had an annotated note on this. Oh, there it is. I was forgetting something. Syn addition. Note 1, 2, 3 at the top, 1, 2, 3, 4 at the bottom. The top one doesn't have syn or anti-addition. I just want to reiterate, it doesn't need it because this is a reaction you have to know. There's no syn or anti-addition. Okay. Syn addition. All right. Syn addition of our OH and our H. Then let's not forget about that methyl group that was over there. All right. Notice the OH went to the least substituted carbon. The H went to the most substituted carbon. Syn addition. That's all we do. All right. Let's move on. MCPBA. This one's fun. Let me make a little bit more room for MCPBA because of how yummy it is. Like Dr. Berg said, you will see this on the MCAT. MCPBA, you will have to know that reagent. You don't have to know the name. You don't have to know the structure. Just know what it does for the most part. So it adds an epoxide across that double bond. Okay. So first off, it's an addition. So if it's an addition, it retains stereochemistry. It's an addition. It's concerted. That might be it. Shift, no shift. You can't shift the triangular structure of the epoxide. And you're just adding an O. So what you do is that literally we add the epoxide. We just add the O and just put it across a double bond. And to give you another reaction with some stereochemistry, because that's too easy. That's too good to be true. If you see that on the test, you're lucky. Because what if you had something like this? Okay. All right. If you just draw that, that's wrong. You need stereochemistry. All right. That's the big thing we have to do. If there's stereochemistry, you need to draw it. If there's not, you can just ignore it. And you might think, what has stereochemistry? What doesn't have stereochemistry? Well, that's what this video is for. Stuff you have to draw on your flashcards. So if this is cis, it retains stereochemistry because it's in addition. All right. So remember, these are methyl groups. There's some hydrogen groups right here. Okay. With that in mind, what I would honestly do, redraw it on the side. Let's imagine I redrew this on the side. I'm just going to add that O right across here. And whatever methyl group I have, let's just draw that stereochemistry. If they're cis, they're going to be cis in that product. And then the H is over here. So our final product would be CH3, H, H, CH3. There you go. What if it was trans? Let's throw a trans one at you. Okay. MCPBA. All right. Drawing something like this. That's incorrect. You can do, literally again, erase this double bond if you redrew it. And then this trans, it retains trans stereochemistry. So that methyl group is wedged and this one is dashed. So I would redraw it. All right. CH3, CH3, and I draw the respective. You can't read that. It doesn't really matter. H and then respective H. Another acceptable way of doing this is in a Hayworth structure. So if you have, let's say, this Hayworth structure. All right. CH3, CH3, H, H. It shows that it's trans, perfectly acceptable. Don't worry about it. We like that. You show that's trans. You'll see that and when we get to stereochemistry, there's R and S and all that stuff. You'll see it, but that's acceptable. Okay. That's oxidation. Now let's get to ozonolysis. O3, negative 78 degrees. And not only that, you have to know the, what is it? The solvents. Even I'm blanking on it right now. I think, what do we need? Zinc. No. Yeah. Zinc. Oh, I did not write it down. Oops. I don't know at the top of my head. That's embarrassing. Okay. Zinc. I think there's another one where it's just like dimethyl sulfur, sulfate, sulfur, something, whatever. You guys can look it up in your notes. But what I'm trying to show you is what you do on your flashcards. Fill it in your flashcards. The first one, you just add an O across a double bond in a weird way. All right. There's no stereochemistry needed, and you'll see why, because it's pretty funky, but also pretty cool. This is a bad example to start off with. Let's just do this. Ozonolysis is really easy. It's kind of like MCPBA. All you do is like snip it across here. Like take some scissors, just snip it across a double bond, and then stick some O's there. You don't have to know the mechanism, but literally your products are going to be this and this. And you can see we just added the O's across the double bond. Another example, what if you had like something like this? Well, look, snip it down here, you get O, literally. Let's bring that old thing back. Cyclohexene. All right, snip it across here, O right here and O right here. And keep in mind, that's the same product. They're still connected by these carbon bonds in a ring structure. So your product would be something like this. Another acceptable thing would be if you stretch it out. As long as the the number of carbons is the same and you added it, they're the same thing. Either one is accepted. You just have to know, all right, we're just adding O's across the double bond. Okay. So I have to know for now. Let me pull up the problem set real quick. Okay, I missed one more thing, and then you should be able to complete your problem set and make your flashcards. All right. What if you had carbon like this? Now, CH3, 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 CH3. Okay, and you had HBr. What will it add to? Well, look at this. They're both tertiary. And you know that the nucleophile, the Br, would want to go to wherever the most substituted carbon is, because you know that reaction is Markovnikov. Well, if they're both the same, what do? You get two products. Simple. I'm just going to leave them as lines, make it easier. H. So like these blue lines, they're connected to the methyl groups. H, Br, Br, H. Even, or you just have to focus that, like, okay, the bridgehead carbons are both tertiary. What if you had, this was a ethyl group, CH2, CH3. All right, that doesn't change anything. All right, the fact that both of these are tertiary doesn't matter. Okay, C, 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 CH2, CH3. Those C's are methyl groups. It doesn't matter. Shift doesn't need to happen. They're both tertiary. If both bridgeheads are the same, you get two products. And nice little hint, if you have like your test page, right? Let's say like you have a predict the product page that's pretty much identical to your problem set. Okay, so you have something like this. Question 1, 2, 3, 4, 5, 6, 7, 8. I know it's inconsistent, but let's just leave it at that. Well, if 9 is this entire box right here, you're probably gonna get two products. It's a long box. It's kind of self-intuitive. If you get a long box, you're probably gonna get two products. All right. So hopefully this helps. If you have any questions, feel free to email your TA or DM them through group if they have GroupMe. If it's Friday night and you're asking questions, good luck, because it's Friday night. The TAs don't really want to be thinking about the problem set like at 10 or 11 p.m. So if you have questions, come to office hours tomorrow, Thursday, do all that stuff. Good luck with your flashcards. We have a lot more, or not a lot more, but we have a good amount of content still for test 2. So yeah, just put in the work and good luck.